Okay, today I'm going to teach you how to write a program that does a Fourier transform to turn a raw waveform, usually in the time domain, into the frequency domain. So how to see, for instance, if you record a sound file with a microphone, what are the frequency components of the sounds you recorded, like of a musical instrument or something. This is the kind of simplified equation that we got to in class. Remember the kind of normal Fourier transform formula that you'll find is an integral of an exponential function with an imaginary number in the exponent. In order to process that on a computer, we've turned the integral into summations, and we've broken up the real and imaginary terms here. You don't really need to keep the real and imaginary information if you're just looking for what's called the power spectrum, which is what are the relative amounts of each frequency of wave present in the wave you're analyzing. The real and imaginary terms tell you the phase information of those frequencies. So where shifted in time those frequency components are relative to each other. And for most applications, you don't want that. We don't want that anyway. So we just need the magnitude of that complex vector, which will be this squared, absolute valued, plus this square, absolute valued, square root of all that. So like the Pythagorean theorem of, if this is your x-axis, this is your y-axis, we want the hypotenuse. Okay, so anyway, let's do this. And there's a couple ways we could get our wave to do the power spectrum of. One, we could record the sound directly from the microphone in LabVIEW by going to graphics and sound input, acquire. It's pretty handy. Feel free to write that program if you want, but we actually want to open a pre-saved wave, which you can do by going to File, Input, Output, Read Delimited Spreadsheet. So this will be able to open tab delimited text files, or even comma delimited text files if you change this delimiter input down here, which is normally a it's normally a tab. It's by default. But we could type in a comma here if we wanted to open a comma delimited text file or some other delimited text file. Anyway, the file I want to open is tab delimited, so I'm just not going to wire anything there. Normally, if you run this, it will kind of open up a file browser, so you can pick the file to open. I'm just going to hardwire in a file path control. So I'll right-click on that terminal, make a control. It'll appear in my front panel. Then I can just open the file once and not have to re-find the file every time I run the program. So when you do that, well, let's see what we get here. The all rows will, if we create an indicator for the all rows output terminal there, we'll get a two-dimensional matrix of our spreadsheet. So if I run that, you can see how this data was saved. We have a column of time points. These are evenly spaced by millisecond, and a column of amplitudes, which should change over time. Yep. And we need both the amplitude at each time and the time itself in order to calculate this Fourier transform. We're also going to end up plotting our Fourier transform over frequency instead. So that's going to be our new independent variable. So we need to generate our frequency points. And then you do that the same way that you did the make x points in the previous program. You can choose any spacing between f points you want for that. So here's our frequency loop. That's going to be our independent variable. we need to multiply that by our df, whatever our spacing is between our f points is going to be. And like I said, you can choose anything for that. But if you choose too poorly, you will undersample or oversample your data, and your frequency spectrum won't be as good as it could be, or it'll have artifacts in it. So the safest number to choose here is the inverse of the total time duration of your wave here. Okay, so this is 3 seconds of recording here, so the df should be 1/3, basically. Rather than just type that in, because that's only specific to this one time file, we want to actually calculate it from these points. So first thing I need to do is break up this two-dimensional array into two one-dimensional arrays, one for the time and one for the amplitude. So if I go to array, index array, that's how you read any value out of an array, or a two-dimensional array, or a three-dimensional array, or whatever it is. You can see there are two index inputs. If I only wire a constant to, say, the row, say if I put in a 0 for the row, this will return this row as a one-dimensional array. If I only wire in a column index, say 0, it'll only return this column as a one-dimensional array. If I wire an index for both, that gives me a row and a column, and I can read a single point from this 2D array. I want the columns. That first column, which is index 0, everything starts from 0 in the programming world. And I also want the second column, which is index 1. So 0 is the time, 1 is the amplitude. From the time, I want to calculate how much time has passed. To do that, I'm going to calculate the dt, the how much time increments between each point, and multiply it by the total number of points. I'm not just gonna, I mean, for this particular example, I could just grab this last time point, but what if our time didn't start at 0? What if it was on some other clock? So this is a safer way to do it. The only assumption here is that all the time points are evenly spaced, which, you know, they will be if you're acquiring this digitally. So I'm going to do another index array that I'm just going to wire this time point array into. And I'm going to grab the, I'm going to take the difference between the first and second numbers there. Okay, so index 1 is going to be the second number. Index 0 is going to be the first number. And I can use a subtract to take the difference. That gives me the dt. How do we get the total number of time points? If you go to array, array size, take our time array, wire that in. That gives you a number, which is the size of the array, just how many numbers are in that array. So we want to multiply the size by the dt. That'll give us the total duration. And I want to take the reciprocal of that, 1 over that time number, to give us the df, the how much the frequencies are going to increment each loop here. Okay, similar thing. How many frequency points do we want? You want 1/2 the number of time points. The reason we're taking 1/2 is because the second half of the points are going to include imaginary information, which, because we're only looking at magnitudes, is just going to be, it's going to be redundant information. It's going to be nonsense. So we want to just divide that number by 2. All right, so now we're making all the frequency points. And now, for each frequency, we need to do these sums over time. So we're going to need another loop. We're going to need to loop over time in here. And for every time point, we want the amplitude and the corresponding time. So we want to grab our data that we read in from our file. Here's our times. By default, it's going to index on this outer loop. It's not what we want. We want to disable the indexing there because we want this inner loop to loop over every single time point, not the outer loop. And you might start getting confused about what all these wires are. So one thing you can do is add labels to your program. If I double click on the background there, it'll open up a little box that I can just type text in. So I could say like time points to label that array. Or better yet, just so it's consistent with our formula, I'll call that T. And down here we can call this A of T. This outer loop is our loop over frequency. This inner loop is our loop over time. T. Okay, and I want to make sure that this amplitude is indexing on time too. Now we just need to calculate these terms here. So for the real term, we need to multiply 2 pi times f times t, take the cosine of that, then multiply by the amplitude. It's like several multiplications in a row. So instead of using several multiply functions in a row, I'm just going to use this compound arithmetic. I'm going to change this from a add to a multiply. Then I can drag it down and I can multiply any number of numbers together. So I need to multiply the frequency, which is this. We just calculated that from the eye of our outer loop, so I'll label that too. There's your frequency. Frequency times time, that's this array, times 2 pi. There is a constant for that, I believe. Math constants, 2 pi. Easy. And then take the cosine of all of that. Go to mathematics, elementary, trigonometric, cosine. Multiply that by A, amplitude, and sum that over all time. Each iteration of this loop is only calculating this term for a single time. But if I auto-index this outside of the loop, I get, all this calculation for all time, and I can just sum all of the numbers in that array, which is this add array elements function here, which will turn that array into a single number, the sum. Okay, now let's do this other term. It's the same thing, 2 pi times frequency times time. We've already done that calculation right here, so no need to do it again. But we need to take the sine of that value instead of the cosine, so we'll go to mathematics, elementary, trigonometric, sine, wire in that 2 pi times f times t, multiply that by A, and then sum all of those, and we're almost there. And we've got these sums. Now we need to square each of these terms. The absolute value would be important if we had left the imaginary number in here, but we didn't, so square is going to be positive anyway. square those, add them, take the square root, and there we go. Those should be our amplitudes in frequency space. So what we want to plot is f versus a of f. So I'm going to go to cluster, bundle the f points, the amplitude points. I'm going to make an XY graph. And maybe our program will work here. If it works, we should get one peak at 10 hertz, because that's what this input file has. And it looks like we did. So if I zoom in on this, there we go. We got the one peak at 10 hertz. I should make sure my axes are labeled properly. This is actually frequency. This is the frequency spectrum. We also actually, instead of just displaying these points, now that we know that works, I'm just going to delete that. Let's also make a graph of our raw waveform so we can see what this Fourier transform did. So I'm just going to make another XY graph here. Can call that the raw waveform. This will be in time. And we can just bundle together these values we read directly from this text file. The time and amplitude points. And that's what we're Fourier transforming. So that the way this was generated was to take a 10 hertz sine wave, which would just be, you know, even amplitude across all time, and multiply it by 1 second wide Gaussian function to make a pulse. And what you should know is if you want to localize a wave in time, remember you need a range of frequency values of sine waves at different frequencies superimposed together in order to make that pulse. That's the uncertainty principle. So why do we only have one peak here? Well, notice that this peak has some width to it, and we're actually using frequencies between 9 and 11 hertz here summed together to make this pulse. You can see the uncertainty principle if I use a longer duration. Let's turn this off, this auto scale off, so you can see when I open this 3-second pulse, this longer pulse. See, now this is going on for a longer period of time. The peak in the frequency spectrum gets narrower because you don't need as wide of a range of frequencies to sum together to make that longer pulse. So a little demonstration of the uncertainty principle there. One other thing I'll show you how to do is, let's say you wanted to save this frequency spectrum. So we've read the raw waveform from a text file. Maybe we want to save the frequency spectrum as another text file. And just go to File, Input, Output, and now we want to do Write Delimited Spreadsheet instead of Read. We need to get our data in the form of a 2D array again. Right now it's just two 1D arrays. So if we go to Array, Build Array, we can combine these X and Y values into a two-dimensional array, wired into the 2D data there. And this will prompt us for a file name to save to when we run it, and it'll save that file. When you do this, by the way, by default, this will actually save the time and amplitude data as rows instead of columns. If you want to switch that, because normally the convention, if you opened it in Excel or something, is to have it as columns, you can go down to this bottom input, which is transpose question mark. By default, the value is false, but if you switch it to true, you'll transpose your matrix. So you'll switch the rows and the columns, and that'll make it look like how you want. So that's how you would save the data. Okay, that's how you make do a frequency analysis, and how to read and write data from text files.